As you watch roller coaster physics, keep these questions in mind.
How do rides create the illusion of increased or decreased weight?
How do the basic laws of physics allow a ride to accelerate?
You may like roller coasters because of their fun factor, but there's a lot of science that goes into designing these hills of thrills. What do you like about roller coasters?
Well, I think roller coasters are fairly nauseating.
On a roller coaster, you can feel like a pilot, in the cockpit of a jet fighter, with the G-forces and the twisting and the flipping.
I used to be scared of roller coasters because I thought when you went upside down, you'd fall out. But now I know with the centrifugal force and with the guarding rails and stuff, it's pretty safe.
When I was on a roller coaster, I dropped a penny and I saw it floating in front of my face because it was dropping as rapidly as I was.
You notice that everybody else is really, really afraid. And like for me, I'm not afraid. I'm just really happy and excited that I'm on it.
I especially like the stomach drop after going over a huge hill.
You get the adrenaline pumping, you get butterflies in your stomach, and then you do it and you're not nervous anymore.
Friction. Potential energy. Gravity. Acceleration. Prepare to be glued to your seats for a short lesson in applied physics. For many otherwise level-headed people, it's the feeling, the heart race, the stomach churn, the sensation of speed, weightlessness, even danger. Chills, thrills, and thrills are what roller coasters are all about. But no matter how big, how fast, how twisted or terrifying, all coasters obey a few basic rules of physics. Take the Mantis at Cedar Point, Ohio. The tallest, the fastest, the scariest stand-up coaster in the world. The first drop is 42 meters. The first loop is a 36-meter vertical. A 31-meter dive, and then a 360-degree bank turn. Before you're done, you hit another loop 25 meters across, angled at a stomach-wrenching 45 degrees, and go headlong into a high-velocity corkscrew. And all of these spine-tingling maneuvers are possible because the designers stayed awake during physics class. Most of these extreme machines don't use engines or motors after the initial ascent, but there is work involved. The coaster's lift chain exerts a force on the car as it slowly hauls you up that first terrifying hill. Since the displacement of the cars is in the same direction as the force, the coaster stores more and more energy, potential energy, the higher it goes. Then gravity takes over. Potential energy becomes kinetic energy. No matter how many loops, hills, or corkscrews to come, you have all the kinetic energy you need for the ride by the time you reach the bottom of the first hill, provided one thing: that none of the subsequent hills or loops is higher than the first one. To be more precise, the roller coaster can never go higher than what Galileo called the stop height. The 16th century astronomer hypothesized that if you start a marble here, it will always roll to the same height no matter what the shape of the track, as long as there are no resistant forces. If there's friction or air resistance, the same principle applies, but the marble stops at a lower point. If roller coaster engineers didn't obey this principle, these thrill rides would be a real snooze. All hills after the first hill have to be low enough so the roller coaster doesn't stall out. And loops can't go higher than the stop height, or the coaster won't have enough energy to make it all the way around. So all these construction details aside, why does plunging over a hill or speeding along a track give us such a thrill?
Dr. Edward Beckman of the Navy's Aviation Medical Acceleration Lab at Johnsville, Pennsylvania, looks like some man from outer space. A giant centrifuge that makes a Coney Island spin seem like child's play. Forces many times those of gravity are exerted.
The secret lies in the inertial effects, popularly known as G-forces. That gives people the sensation of increased or decreased weight. Newton's first law of motion says that objects such as you in your roller coaster seat move in a straight line at a constant velocity unless acted upon by an outside unbalanced force. When the roller coaster goes around corners, your seat provides an unbalanced force, accelerating you around the corner. Your seat pushes against your body as your inertia tries to keep going around the corner. At this time, you feel momentarily heavier. You're experiencing positive G's.
The G-forces that you suffer on a ride like this go up to about 4G positive and about half a G negative.
On a roller coaster, positive G's deliver most of the thrills. When you near the bottom of a hill or go into a loop, you experience positive G's. Every ounce of your body, including your blood, feels several times heavier than normal. Not just to you, but to your heart. If your heart can't generate enough force to push this heavier blood to your brain won't get enough oxygen and you'll black out. This near blackout sensation creates a sense of danger, giving you a real rush. The opposite of positive G's is, you guessed it, negative G's. When you approach the top of a hill and the car slows down, inertia would send you flying out into the sky if you weren't buckled to your seat. As your inertia attempts to carry you up and out, there is less pressure between your bottom and the seat. Your brain interprets this as less weight, and in some cases as weightlessness, also known as negative G's. Suddenly, your blood is light for your heart to pump, almost too light. Too many negative G's can cause a readout. Too much blood rushes to the brain. Your blood vessels could even burst, a fatal result. That's definitely not the kind of head rush you're looking for.
Lashed to the center post, the cameraman films dizzy doings as the more daring of the rotor riders defy centrifugal force, or try. The rotor ride is a snap, unless you're the squeamish sort.
All roller coasters are designed to subject you to as much positive G-force as possible, because the body is much better at coping with it than negative G-force. 4 G's positive, though, meaning that your whole body weighs 4 times more than normal, is about the limit.
The human body reacts very badly to large G-forces. At about 6G, then most people's noses will begin to bleed. At about 10G, a lot of passengers would actually pass out.
At 14 G's, you'd probably die. That's helpful to remember if you hope to become an astronaut or a pilot. Just ask Sean Tucker.
Pulling G's on these extreme rides are quite similar as to what I experience on my aerobatic aircraft. In fact, some of the abrupt changes are a little bit more. And if you're hooked on G's, this is a lot of fun.
Like on a roller coaster ride, the aerobatics pilot experiences both positive and negative G's.
Positive G-forces are what we experience here on Earth as 1G. In order for me to experience the freedom of flight, to loop an airplane, to fly upside down, I have to go through many different variations of G-forces. I'll experience sometimes 10 positive Gs, 10 times my body weight during an aerobatic maneuver. In order not to become unconscious or black out during high G-force, positive G-force maneuvers, I need to tighten up my neck muscles, tighten up my stomach muscles, my leg muscles, and my butt muscles, and really grunt to go through the high G-pull. And during my aerobatic routine, I'll experience 8 to 9 times my body weight. A negative G is something that when I'm flying upside down, the gravity wants to throw me outside of the cockpit. Just as you might experience on an extreme ride, I take the airplane and tumble it end over end through the sky in a big old corkscrew, and I'll dive back down towards the ground and pull up, get upside down, come back up in a great big huge old loopy maneuver and see the whole world, and we'll come back around again and corkscrew some more.
G-forces in the air versus G-forces on the ground.
Let's make a few comparisons.
Let's do a loop. Here we go. Pull it up. Over the top. We're weightless. Slowly coming back around. Here comes the ground. Get ready to tighten up. Pulling G, and level. How about a corkscrew? Here we go. Snapping now. Look at that Earth go around. And recover.
We now go from cockpit to coaster. Batman. The ride at Six Flags Magic Mountain, California gets tested by an expert.
Okay, here we go. Climbing way up into the sky. Well, we'll see if this ride is really like flying. And to start out with, it is, because we got to climb up to get our altitude so we can dive back down to get our airspeed to do an aerobatic maneuver. You know, I live for G's. Diving down. Yeah! I like it. Yeah! Whoa! I like this. Diving up for airspeed, pulling G's over the top weightless. Whoa! Gives us made a real corkscrew. Yes! Yes! It's quick and it's tight. Good G. Woo!
Sean may be having a good time, but in reality, the positive G-forces he experiences on Batman the Ride don't compare to the 10 positive G-forces a pilot can experience. In fact, in the U.S., engineering standards forbid any coaster from subjecting riders to more than 3.5 positive Gs.
Viper at Six Flags Magic Mountain is typical of a modern roller coaster. Lots of twists, loops, and corkscrew, and the inertial effects they produce. In fact, if blindfolded, you'd have a hard time telling when you were upside down. Believe it or not, all these loops and corkscrews are a kind of safety feature, making the ride barely bearable. They slow you down just enough to keep the G-forces extreme, but not dangerous. But extreme is what we want. The question is, why do we enjoy it so much?
People who are constantly seeking thrills have been found to be low in a particular brain chemical called monoamine oxidase. Now, this is an enzyme responsible for modulating the neurotransmitters concerned with arousal, sleep, mood, and pleasure. People who seek thrills apparently need a greater level of stimulation to maintain their brains at a level of arousal that is most comfortable for them. Whenever we're subjected to stress, as in a sense you are on a roller coaster, then another chemical is produced in the brain called endorphins, which mimics morphine-like substances. Very pleasurable, euphoric chemical.
A word of caution. These rides are not for the faint-hearted. Extreme activation of the nervous system can trigger physical problems, including a drop in blood pressure that can stop the heart. Technically, you can die of fright. Yes, the laws of physics can be a matter of life and death, and not just when you're being tested on them. As you're winched up the first hill of the big one in Blackpool, England, for instance, 72 meters above the ground, it's worth remembering that roller coasters are very flexible. They can even sway in the breeze. And with all the terrifying twists and turns, those positive and negative G-forces can cause some people to feel a bit worse for wear. The illusion of danger is thrilling, but the potential is very real. So, how do designers keep physics from becoming a physical menace? For starters, there are 3 sets of wheels on every roller coaster, which combine to effectively clamp the train to the track. Running wheels support the cars and are responsible for the speed along the top of the track. Upstop wheels are mounted beneath the track to prevent you from crashing to the ground when upside down or flying off when going over hills and loops. Friction wheels are mounted on the inside of the track to hold the train's side-to-side motion. This system makes it impossible for a car to leave the track, even under the extreme stresses of a ride designed to take you to the limit. But it won't do any good to keep the cars on the track if the track isn't safe. That's why each day at Cedar Point, Ohio, all rides are checked hours before the thrill seekers arrive.
Every morning before the parks open, we walk the ride for 4 hours, inspecting the track and the structure to make sure that everything's in operation.
It is a well-known law of physics that for every action, there is an opposite and equal reaction. Just as the car and rider are subjected to unbalanced forces as they accelerate through twists and turns and hills and valleys, reaction forces are experienced by the coaster. These forces eventually take their toll, causing rivets to pop, bolts to shear, welded joints to crack, and wear and tear on wheels and bearings. Technicians and engineers must look carefully for these telltale signs of physics at work. In 1996, something serious appeared at Six Flags Magic Mountain, California. Something big. Very big. Extremely big.
Superman the Escape is the world's tallest and fastest roller coaster. 100 miles an hour and 411 feet straight up.
The builders of Superman the Escape decided that the old formula wasn't good enough. This is one coaster that doesn't coast.
Basically, the power system consists of what we call a linear synchronous motor that generate about 2,000 horsepower that can accelerate the train up to 100 miles an hour and 700 feet.
Linear synchronous motors, powerful electromagnets in a line of posts down the center of the track, repel opposite magnets mounted on the cars. When activated, the magnet on the first post pushes the car down to the next post, and so on, accelerating it at increasing speeds along the track.
The magnet propulsion system also serves as the magnet braking system. We switch the linear motors into what we call a short circuit. Basically, the generator becomes the power system. As a result of the acceleration, we have to burn off an enormous amount of energy on the return cycle, and the energy is burned off in heat.
Full-on, in-your-face excitement. And roller coaster builders are always looking for ways to make them bigger and faster. But what are the physical limits for rides of the future?
In terms of speed, well, there are lots of limitations on speed. At the moment, small wheels require very fast rotational rates in order to get high speeds. That means very high speed bearings and so on. The higher you go, the faster you will go when you come down, and therefore the larger the wheels need to be. So you end up with wheels that are getting of the order of half a metre or even a metre in diameter in order to cope with the very high rates when you go to 100 miles an hour or more. And this is one of the main problems.
So if you can only go so fast, where else is there to go? How about straight up? In Las Vegas, where no one plays it safe, pushing the limits of physics is delivering new thrills. The Big Shot, 0 to 108 kilometers an hour in 3 seconds. One express elevator to terror, going down. As you bounce to an eventual stop, there's plenty of time to savor the fact that you're more than 305 meters above the streets below. The Big Shot uses a system of compressed air pulleys and guide wheels to propel its unfortunate passengers to a new high. The same system cushions you at the end of your 20-meter freefall. Yet despite all the high technology, it's just inertial effects disguised as gravity. And in this case, negative G's that deliver the thrills. The use of computers both in design and construction means that roller coasters are destined to get faster and more complicated and thrill you more than ever before. So what can we look forward to in the future?
No comment. I'm not going to tell you.
Coaster designers may not be willing to reveal trade secrets, but one thing is certain. They may try to exploit the laws of physics. They may try to challenge the laws of physics, but they can't change the laws of physics. Gravity, friction, inertia, potential and kinetic energy, speed and momentum will all be part of the equation.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
How do rides create the illusion of increased or decreased weight?
How do the basic laws of physics allow a ride to accelerate?
If you'd like to learn more about what you've just seen, go online or check out these books at your local library.